This is in preparation for my book. And the tentative title right now is a working title, so don't worry about it, but it's Considering Einstein and the Quantum Theory. A subtitle, The Physics Behind an Apparitional Universe. And we'll see how far we get in part one. I was very ambitious and I thought we'd get from the dawn of modern science to special relativity, but I don't think so. And I should also point out that a lot of the ideas you're going to hear are based on the cosmology of John Dobson, who was the founder of the San Francisco Sidewalk Astronomers and the inventor of the Dobsonian telescope. So, I'll just lay it out. The Quantum Enigma. Quantum theory has been tested for over 85 years. No prediction by this theory has ever been shown to be wrong. But if you take this theory seriously, it says that the reality of the physical universe depends upon our observation of it. This is the quantum enigma. It seems almost impossible to comprehend, and Sir James Jeans said, quote, "The universe begins to look more like a great thought than a great machine." So, to explore all this stuff that we're going to go into, we have to have some ground rules. The first ground rule is that we're going to employ the scientific method. This is a structured method of inquiry. It's based on gathering observations. It's empirical, looking for measurable evidence that's subject to specific principles of reasoning. It consists of collection of data through observation and experimentation, and then the formulation and testing of hypotheses. And these steps need to be repeated by anyone. And the hypotheses must dependably predict future results. Second ground rule, we'll employ what's called Occam's razor. The simplest explanation that covers the facts is usually the best. That's a quote from him. The theory with the fewest new assumptions is usually the correct one. Entities must not be multiplied beyond necessity. That all came from Father William of Occam. I don't have the date, I should. Sir Isaac Newton put it in his Principia as, "We are to admit no more causes of natural things than such are both true and sufficient to explain their appearances. Therefore, to the same natural effects we must, so far as possible, assign the same causes." It will become apparent later why Occam's razor is very important. And then the final ground rule is that we need to trust the equations of physics and science, not our common sense. And I don't have this figured out here, but I was going to actually start the book by describing a pilot, like myself, who is only trained to fly in good weather. And if such a pilot who's not trained to fly on instruments loses sight of the horizon by flying into a fog bank or a cloud, or because it's dark at night and there's no moon, and there's nothing to give him any sense of a horizon, and he trusts his guts to keep the plane level, he will kill himself in about 30 seconds. He will put the plane into what's called a dead man's spiral, thinking all the time that the plane is perfectly level, when in fact it's banked slightly, and it will continue to turn that plane at a point where it'll just spiral. It's a well-known phenomenon. It's very likely what happened to Robert Kennedy Jr. But the point is that in the plane are instruments. And if you are instrument rated, you've gone through training that does two things. One, you know how to interpret what the instruments are telling you about where the horizon really is. And more importantly, you trust the instruments, not your guts. Otherwise you'll kill yourself. And I believe in the world of quantum physics and Einsteinian theory, if you are going to be honest, you have to realize that the common sense view is not correct, but the equations suggest a viewpoint very different that will go against your common sense. Nonetheless, the equations are what we have to trust, not our guts. So, how do we know our universe? By observation. How do we observe the universe? We see things away from us. We do that via radiation, light energy. We hear things away from us via sound energy. We touch, feel things separate from us. That's really based on electrical energy. And we taste, smell things separate from us. That's actually based on our sensing of magnetic bonds. The interesting thing about all of these observations, these 5 sense phenomena, are all electromagnetically based. So, the 5 senses that we have respond to 5 different kinds of energies. The inner ear, the saccule, responds to gravitation. It's how we get oriented in the gravitational field, and it is, by the way, what gets confused when you're in that airplane without a reference to the horizon. Our skin responds to kinetic energy. Temperature is kinetic energy. When you rub your hands together, things get hot. That's kinetic energy being turned into heat. The eyes respond to radiation energy, but only in a very select band of frequencies. The tongue responds to electrical energy. Protons, single protons, taste sour. And the nose, a very complicated mechanism, responds to magnetic energy in sensing the molecular bonds of various smells. So, what can we observe about the universe? Well, it appears as made up of really itsy-bitsy, teeny-tiny, electrically charged particles of matter that always want to fall together by gravity. Our universe and everything in it appears to be bound by laws of gravity, inertia, and electricity. But those particles of matter also appear as waves. How can we explain this? Well, actually, we can't. We don't know why all the bits of matter exhibit gravity, electricity, and inertia. And we still don't know what gravity, inertia, and electricity really are. So, how did these concepts of gravity and inertia first arise? We're going to go through a quick history, starting with Aristotle and the Greeks. Jump ahead to Nicholas Copernicus, and Galileo, Tycho Brahe, or Tycho Brahe, I don't know. Johann Kepler, and Sir Isaac Newton. So if we start with the philosophers of ancient Greece, they actually set the stage for modern science because they saw nature as explicable. They saw nature as governed by laws. And they actually defined the laws of logic. And they sought explanations based on fundamental principles. Aristotle chose some fundamental principles. First, the earth is the center of the universe. All heavenly bodies move in perfect circles. Objects fall because of their desire for the cosmic center. Heavier objects will fall faster than lighter ones. And the stuff of the universe is made of 5 elements, actually 4 plus 1 elements. Earth, water, air, fire, and ether. The first 4 elements were earthly, the last one, the ether, was not. So Aristotle's common sense view was, he said, matter cannot act where it is not. Which is to say, matter can't interact with any other matter unless it is somehow in direct contact with it. And it's interesting to note that Einstein felt exactly the same way. He had an unyielding bias that matter had to be touched by something in order to move.
Can you explain that?
Well,
what did Aristotle mean?
He meant that if you saw an arrow moving, it was being propelled along somehow by something pushing on it.
Okay.
any movement you saw had to be as the result of a direct contact. If you think about mechanics or anything, I mean, initially, you know, with the arrow, you have the bow and it launched it, but there was a direct
Action.
direct action, direct contact. And matter is not going to move or stop moving unless something acts on it that touches it somehow. So Aristotle's major mistake was that he assumed these fundamental principles could be intuitively perceived as self-evident. And so his science had no mechanism to compel consensus. In other words, these things were not to be tested. They were just obvious. Later, the Catholic Church made a mistake too, because they picked up Aristotle's view and it became the official dogma of the Catholic Church in the late Middle Ages, and it was primarily through the efforts of Thomas Aquinas. Aquinas took Aristotle's cosmology and his physics, and he fit it together with the Church's moral and spiritual doctrine. For example, Earth, where things fell, was also the realm of the morally fallen man. And the heavens, where things moved in perfect circles, was the realm of God and his angels. Now, Pythagoras felt that the universe was a flawed reflection of perfection. And of course, we have the Pythagorean theorem as a way of measuring the distance between two points. Ptolemy of Alexandria was trying to solve problems for astrologers. The astrologers needed to track and predict the 5 bright objects, which we now know as the planets. They were called the wanderers, that wandered through the sky. You had fixed stars, and you have these 5 objects that were moving. And they watched them very closely because that's how they would make their astrological predictions. So it would be helpful to have a way of doing this mathematically. And Ptolemy's mathematics, his model of the universe, worked beautifully. But it required that the planets move on epicycles. These were really complicated, loopy curves and circles within circles. Of course, the stationary Earth was at the center, cosmic center, but it worked. It at least tracked and predicted the motion of all the objects, including the sun. And it was accepted as true, and then later this became religious doctrine. Excuse me.
You don't mind.
No, it's okay. So, Nicholas Copernicus, late 1400s, early 1500s, was a Polish monk. He was born 1400 years after Ptolemy. That's how long Ptolemy's ideas held sway. In 1543, his treatise, called The Revolution of Heavenly Orbs, was published right after his death. And that was by design. He did not want to take on the church or any authority. But in his treatise, the sun, not the earth, was the center of the universe. All the other 5 planets orbited the sun. He also points out that the earth spins on its axis, and that it was the 3rd planet from the sun. The heavenly bodies still traveled in circular orbits, but this was a much simpler explanation of the observations. Keep in mind Occam's razor. The simplicity of what he came up with was not sufficient to win over the authorities. One of the ways that he was ignored is that they would say, look, the earth obviously stands still. We don't feel any motion. If it's in motion, we would feel it. And it was also perfectly obvious that if you took a stone and you dropped it, it obviously would be left behind if we were dropping it on a moving earth. The earth would move away. So, boom. And since air occupied all of space, a great wind should be blowing if we're on a moving earth. So these are the kind of arguments to justify keeping the status quo. But most importantly, the Copernican viewpoint conflicted with the, quote, wisdom of the golden age, unquote. They contradicted the Bible and they put salvation at risk. Johann Kepler came a little later. He was the first to coin the term inertia from inert. But he came to the conclusion that the sun and the earth attract each other, and so do the earth and the moon. He incorrectly attributed the attraction initially to angels, and then later to magnetism, which also was wrong. But he had the idea of a mutual attraction across empty space, and that too was contrary to Aristotle. Tycho Brahe was a contemporary of Kepler, died before him, but he made very, very accurate observations. And Kepler got his hands on these observations after Brahe died. And that allowed him to resolve his thinking into three basic laws. First, the orbits of the planets were elliptical, not circular, and the sun was off-centered in the elliptical orbit. That led to the idea that the closer the planet was to the sun, the faster it would move in its orbit. And the larger the orbit, the longer it would take for a planet to go around the sun. So it was a brilliant analysis of hard observations. But Kepler couldn't explain these rules. And he didn't like them, because now we had these imperfect circles. But he accepted what he saw. He accepted the observations. There's a fellow named Giovanni Benedetti in the early 1500s, Italian obviously, who studied the flight of cannonballs. So he set out to test one of Aristotle's thoughts, obvious facts. He tied two objects of equal weight together with a thin thread. He expected them to fall twice as fast. And that's what Aristotle would have expected in his idea, because heavier objects fall faster to the earth. So you take two objects, now you connect them. They should fall twice as fast. But he discovered that was not the case. And he confirmed that all objects fall to the earth at the same rate, regardless of their weight. And I point out that that's Benedetti who did this, because Galileo got credit for it. And Galileo also observed the same fact, but Benedetti came up with the discovery before Galileo. Still, Galileo was the first to truly employ the scientific method. He really is the father of the scientific method. He was the first to conceive and carry out experiments to prove his theories. So, at this point I have to go into a description of what Galileo observed about pendulums. He studied them, I think, while he was getting bored sitting through service in church. I think that's the story. You would watch the chandelier go back and forth, something like that. But anyway, he found that the period of one oscillation, one cycle, was constant. It didn't matter how large or small of the amplitude of the swing. No matter how much it moved, it was a constant. He got the same result with pendulums of equal length, but unequal weights attached to them. And actually, these experiments were excellent demonstrations of the force of inertia. So, he came up with his law of falling bodies, and he said, in a vacuum, all bodies fall at the same acceleration. Not the Aristotelian concept at all.
But
yeah,
he didn't have a vacuum.
That's right.
So it
Neither
wasn't
did he.
Observational. It was.
He extrapolated from the observation, but the reason that he said in a vacuum, he wanted to eliminate the effect of air.
Yes.
So to get over that, when he did his famous experiment in the Tower of Pisa, he had objects that were heavy enough to overcome any air resistance. so he could prove the point.
But they were of different weights.
Yes.
Okay.
But the best example of this, and you can find it on YouTube, was when we went up to the moon. They repeated the same experiment, but this time they did it with I think it was a lead ball and a feather.
Mm.
Well, now on the moon they have a vacuum. They both hit at the same time. So that really illustrates the point better than anything else, but that's the brilliance of Galileo and Newton. They extrapolated into seeing these forces operate in a vacuum. They didn't have a vacuum to confirm the experiment. They based it on the observation of experiments that they could perform that weren't limited by the fact they didn't have a vacuum. So, in a vacuum, all bodies fall with the same acceleration. The effect of gravity is the same regardless of the mass of the body. The distance that it falls is proportional to time squared. And the question is, why do bodies fall to Earth rather than fly off into space?